Hey guys, Kenny here. Today we're going to be taking a look at indirect measurement and scaling. Let's go ahead, jump right in and start with our essential questions. Number one, what is shadow reckoning and how does it relate to geometry? Now you may have done some of this in your geometry classes. Think about proportions, okay? So this may not be new for a lot of you. Number two, what is parallax and how do astronomers use it? It's a very powerful tool that we use in astronomy that is based on perspective. And so we'll come to that in a little bit. And then lastly, what is the difference between uniform and non-uniform scaling? Okay, so let's just jump right in. Now, the concept of indirect measurement is attributed to Thales. Thales is known as the first Greek scientist, engineer, and mathematician. According to legend, he was the first to determine the height of the pyramids in Egypt by examining the shadows made by the sun. He considered 3 points: the top of the objects, the length of the shadows, and the bases. Okay. Now, if you take a look at this concept, and you can see from the picture, hopefully that helps, what appears to be true about the corresponding angles in the two different triangles. We'll go back to that picture so you can see. Okay. And then two, if the corresponding sides are proportional, what could you conclude about the triangles? There's the picture again. All right. Now, indirect measurement allows you to use properties of similar polygons. Most notably, what they give you in most of geometry is similar triangles, to find distances or lengths that are difficult to measure directly, things that are too tall or too far away or these types of things. Okay. The type of indirect measurement that Thales uses is called shadow reckoning. We typically will go ahead and use the length of a shadow to go ahead and determine the height of the object by measuring the length of your shadow and how tall you are. Then we can set up proportional triangles, and by using similar triangles, we can go ahead and deduce the actual height of the object, producing the other shadow. Now, he measured his height and the length of his shadow, then compared it with the length of the shadow cast by the pyramid in the equation seen here. This is a pretty standard proportion, and I think you shouldn't have too many problems going ahead and doing some basic proportion problems. Okay, if you do, please reach out to me and we can go ahead and go over it. All right, the next thing I want to talk to you about with this concept of indirect measurement is something that we call parallax. Now, astronomers use an effect called parallax to measure distances to nearby stars. Parallax is the apparent displacement or movement of an object because of a change in the observer's point of view. In the diagram I'll pull up here in a second, as the observer moves between the two positions, he would see the same tree, but it would appear to move with respect to the background. Nearby objects have a larger parallax than more distant objects when observed from different positions, so parallax can be used to determine distances. Astronomers use this principle of parallax to measure distances to the closer stars. Now, you've probably experienced parallax in your life, you just may not know it. Try and think of an example as I go ahead and pull up this image, and then we'll talk about it. In this image, you can see that if the individual moves either from the position on the left to the right or the position on the right to the left, the position of the tree appears to change with respect to the position of the moon, because the tree is closer and the moon is farther away. Okay, this is essentially what parallax is. Now, did you think of an example? Hopefully you did. One common one is when you look at the speedometer, whether you're driving in the driver's seat or sitting in the front passenger seat. The actual reading is different because of the angle at which you are looking at the speedometer, since the speedometer is not fixed to the surface, but typically sits up above it. Okay, so there are lots of examples of parallax, and you could easily set this up on your own. Just go outside at night if there's a clear night and go ahead and look at the moon and do that with respect to, say, a stop sign or something. And then move to a different position, see how the stop sign has changed, but the position of the moon has not. But it appears like the relationship between the two has shifted because it has. Now, the amount that it has shifted gives you some sense of the distance between the two objects that you are viewing. the near object, and the far object. Okay? Which leads to scaling. Now, in physics, it's really helpful to draw diagrams. And when you draw these diagrams, scaling is when you make a relationship between the real object and the object that you are trying to represent. For most of what we do, we are really focused on uniform scaling. Another term for this is what's known as isotropic. Iso, that prefix, hopefully you recognize from isosceles, means equal or the same. And this is a linear transformation that enlarges, increases, or shrinks, diminishes objects by a scale factor that's the same in all directions. So that 1 inch going left to right is the same as 1 inch going up and down, and that represents a certain amount when you go ahead and apply it to the real object. Okay, and that amount is the same regardless of which direction you're moving in. The result of uniform scaling is very similar in the geometric sense to the original. A scale factor of 1 is normally allowed so that congruent shapes are also classed as similar. What you see when you look at the drawing is what you see on some different scale in real life. Now, this happens a lot when we're taking a photograph or if you're building a scale model, whether it's building a car, an airplane, etc. These 1:1 or 1:5 or 1:10 or whatever the scale is, these types of representation are what we call uniform scaling. However, we do have some things that do what's known as non-uniform scaling, also known as anisotropic. An, the prefix meaning not, iso meaning same, and tropic representing the transport of the representation. So not the same, unlike isotropic, which is the same. This is obtained when at least one of the scaling factors is different from the other. The most common place where you'll see this is when we start looking at maps. Okay, this is a special case of non-uniform scaling known as directional scaling or stretching. We're doing this in one direction to make the representation more visible. If you've ever looked at a traditional map in your world studies class or AP human geography, you know that, hopefully you know, that Greenland is not as big as it looks on the map. That's because most of the maps that we use are what are called a Mercator projection, and they stretch the North and South Pole so that you get a nice rectangle. This helps you to make sure you see distances, although they're stretched in the northern reaches. It's not a representation of the way the actual globe works and functions, but it makes it easy to see all of it in a single sheet without having to cut it up into pieces. Okay. So non-uniform scaling changes the shape of the object. A square may change to a rectangle or into a parallelogram, and you can think of a lot of your different maps. Okay. All right. So I have a short little video clip here to show you. I'm not going to show you the whole thing because it's really targeted at a lower audience, but it helps to get some good points across. So here we go.
Hi, I'm Jennifer Pulley, and welcome to NASA Connect, the show that connects you to math, science, technology, and NASA. Today, we are at NASA Kennedy Space Center on the east coast of Florida, and behind me is the Vehicle Assembly Building, or VAB. This is where NASA assembles all the components of the space shuttle system. Kennedy Space Center is also a site where NASA launches satellites that study the Earth and our solar system. In fact, the satellite Voyager 1, which was launched right here back in 1977, is very close to leaving our solar system. It's over 13 billion kilometers, or 8 billion miles, from Earth. Can you imagine that? 13 billion kilometers? Whew, it would be hard to count that high. Just look at all the digits that 13 billion represents. I don't know about you, but it's hard for me to imagine just how far away 13 billion kilometers is. I mean, how large is the solar system? It would probably make more sense to us if we could see a scale model of the solar system. This would give a better understanding of how far away Voyager 1 or the other planets in the solar system are from Earth. The focus of today's program is to learn why we use scale models to determine the size and distance of objects in our solar system and beyond. In order to learn how to scale the solar system, we must first understand the concept of scaling. During the course of the program, you will be asked to answer several inquiry-based questions. After the questions appear on the screen, your teacher will pause the program to allow you time to answer and discuss the questions. This is your time to explore and become critical thinkers. Students working in groups, take a few minutes to answer the following questions. What does it mean to scale? Why is it sometimes necessary to use scale models or drawings? List some math terms associated with scale models or drawings. It's now time to pause the program and answer the questions. A scale model or drawing is used to represent an object that is too large or too small to be drawn or built at actual size. The scale gives the ratio of the measurements in the model or drawing to the measurements of the actual object. Remember, guys, a ratio is a fraction that is used to compare the size of two numbers to each other. Let's take a look at an example. One of the most common types of scale drawings is a map. Maps are very useful when planning a trip, whether it is across town or across the country. Norbert and Zot are planning to drive from NASA Kennedy Space Center to Washington, D.C. Norbert wants to estimate the distance he and Zot will travel. The scale on Norbert's map reads 1 centimeter equals 100 kilometers. How can he estimate the distance in kilometers from Kennedy Space Center to Washington, D.C. using the given scale? The scale can be written as the fraction 1 centimeter over 100 kilometers. The first number, 1 centimeter, represents the map distance, and the second number, 100 kilometers, represents the actual distance. First, using a metric ruler and the given map, measure the linear distance from Kennedy Space Center to Washington, D.C. On Norbert's map, this distance is approximately 13.5 centimeters. Now we have all the information we need to set up our proportion. Remember, guys, a proportion is a pair of equal ratios. The first ratio is the map scale, and the second ratio is the distance from Kennedy Space Center to Washington, D.C. Let's set these two ratios equal to each other. N represents the distance that we are trying to calculate. This proportion can be read as 1 centimeter is to 100 kilometers, as 13.5 centimeters is to n kilometers. In a proportion, the cross products of the two ratios are equal. In other words, the product of the top value from the first ratio and the bottom value from the second ratio is equal to the product of the top value of the second ratio and the bottom value from the first ratio. We can write the cross product as 1 centimeter times n kilometers equals 100 kilometers times 13.5 centimeters. Using multiplication, Norbert calculated the actual distance between Kennedy Space Center and Washington, D.C. to be about 1,350 kilometers. Students, here is an important point for you to remember. Proportions often include different units of measurements. Units must be the same across the top and bottom or down the left and right sides. If the units only match diagonally, then the ratios do not form a proportion. So guys, are you still having trouble trying to understand scaling? Okay, well, let's look at another example. This time,
So I'm going to go ahead and stop it right here. I think you get the general idea. And as we go ahead and look at this, if you need help with this, please don't hesitate to reach out. Come see me. We can go ahead and work on some of these proportions. Make sure you have a good understanding of how to do shadow reckoning. And when you start looking at scales and adjusting scales, it's essentially related to proportions as well. So, all right, I hope you guys stay safe, stay healthy, have a great one. Till we meet again, take care of yourselves. Bye-bye.